All right, let's talk about something that's making huge waves in the AI world. It's an architecture called Mamba. And look, this isn't just some minor update. It's a fundamental rethink designed to solve a massive problem at the very heart of the models that power our world now, everything from ChatGPT to image generators. So, what's the big deal? Let's get right into it. Okay, this might look like some complex computer science jargon, but trust me, this is the whole story right here. This O of n squared versus O of n, it's everything. It basically shows how these two architectures handle more and more information. A transformer's workload, it scales quadratically. That means it doesn't just get slower, it gets exponentially slower real fast. Mamba, on the other hand, grows linearly. That one single difference could completely change the game for AI. So, to really get why Mamba is so exciting, we've got to first understand the problem it's trying to solve. And it's a problem that's baked right into the secret sauce that made transformers so powerful to begin with. I'm talking about the attention mechanism. Right. So the core idea behind self-attention is that for a model to really understand a sentence, every single word has to look at every other word. Now, think about that for a second. With 10 words, that's 100 comparisons. Okay, but with 1,000 words, that's 1,000,000 comparisons. You can see how this just explodes. And that quadratic nightmare is exactly why transformers start to choke when you feed them really long stuff, like entire books or high-fidelity audio, or even something as complex as a whole genome. Now, this isn't a new problem. Researchers have been banging their heads against this wall for years. And one of the most promising ideas actually came from a much, much older concept, a class of models called state space models, or SSMs for short. So what in the world is a state? Well, the maze analogy here is perfect. The state space is like the full map of the entire maze, every possible path, every dead end. A single state is just your current position in that maze. It's a super compressed summary of how you got there and what you know. An SSM works the same way. It keeps a compressed digital state to remember the context, and then it uses that state to predict what's going to happen next. At their heart, SSMs really just do two things, over and over. First, you give it a new piece of info, say a new word, and it updates its internal state, its memory. Then, second, it uses that new, updated state to make a prediction. This happens sequentially, one step at a time, just passing this little compressed state along. And that's what makes them so efficient, because they completely sidestep that whole quadratic comparison mess. Okay, so if these SSMs were so fast and efficient, why didn't they take over the world years ago? Well, turns out they had a pretty big flaw. While they were incredibly fast, they were kind of dumb when it came to understanding complex things like human language. The Mamba creators nailed it in their paper. They said the key weakness was an inability to perform content-based reasoning. What does that mean? It means the models just couldn't tell the difference between important information and, well, junk. They treated everything the same. The fancy technical term for this problem is linear time invariance, or LTI. All it really means is that the model's internal rules are totally fixed. They're static. They can't change based on what you feed it. It's like having a camera with a filter that's permanently glued on. It's going to treat a crucial detail in a sentence with the exact same importance as a filler word like or And that's why they failed so badly at tasks where you have to selectively remember one specific detail from a huge amount of text. And this, right here, is where Mamba makes its grand entrance. The core breakthrough, the genius of it, is a really elegant solution to this static problem. It gives these super fast models the ability to be selective. Here it is. This is the big idea. Traditional SSMs had static parameters. They were fixed, they never changed. Mamba makes those parameters dynamic. They actually change depending on the input data itself. It's a simple concept, but it's incredibly powerful. It lets the model change its own rules on the fly, deciding for each new piece of information, is this important? Should I remember this? Or can I just let it go? And this power, this selectivity, has some amazing real-world benefits. It means the model can learn to just ignore filler words. It can figure out when a piece of context is no longer relevant and just forget it. It can even completely reset its own memory when it sees a clear boundary, like the beginning of a new document.
It basically learns to compress context intelligently, kind of like we do when we're listening to someone talk.
But wait, making the model dynamic and selective like this creates a whole new headache. See, the only reason those old SSMs could be trained fast was because their static nature allowed for a clever math trick called a convolution. Mamba selectivity completely breaks that trick. So how on earth did its creators manage to get the best of both worlds? A model that's both selective and still lightning fast to train? The answer is some absolutely brilliant hardware-aware engineering. Instead of using that old convolution trick, they built a new algorithm from the ground up, designed specifically for modern GPUs. It has 3 key parts. First, a parallel scan that lets them parallelize this inherently sequential process, which sounds impossible, but they did it. Second, kernel fusion, which basically keeps all the math happening in the super fast GPU memory instead of wasting time moving data around. And third, recomputation, a smart way to avoid storing massive amounts of data, which saves a ton of memory. This is the engineering magic that makes Mamba actually work in the real world.
So you take this new selective state space model, you power it with that incredibly clever hardware-aware algorithm, and what you get is the final Mamba architecture. And the results are pretty stunning.
When you put it all together, the final architecture is just clean. It's so much simpler. Instead of a transformer that has to alternate between these complex attention blocks and MLP blocks, Mamba just uses one simple repeating block. And then look at that inference speed. Because it just has to update that one small state, generating the next word takes the same amount of time every single time, no matter how long the prompt was. For actually using these models, that's a massive, massive win.
So, the billion-dollar question, does it actually work? Well, this chart says it all. This shows performance on a key benchmark, where lower is better. And you can see, Mamba doesn't just compete with a highly optimized transformer, it matches or even beats it. This was the moment everyone was waiting for. This was proof that an intention-free model could finally achieve that state-of-the-art transformer-level quality.
And the efficiency gains are just wild. The researchers found that a 3 billion parameter Mamba model could perform just as well as a transformer that was twice its size. Let that sink in. Same quality for half the model size. That is a huge deal. That efficiency translates directly to raw speed. Higher throughput basically means Mamba can spit out answers 4 to 5 times faster than a transformer of the same size. Since it doesn't need to keep that huge, ever-growing cache of past information, it just runs so much faster when you actually put it to work. You know, Mamba isn't just one model. It's a new foundational idea, a new building block. And that idea is already being grabbed by researchers and adapted and expanded into this whole growing family of Mamba-inspired models. I mean, it's really exploding. We're already seeing things like Mamba Byte, which works directly on raw data instead of tokens. There's Vision Mamba, or Vim, that adapts this idea for images. People are even combining it with other hot ideas like Mixture of Experts, or creating hybrids like Jamba, which actually uses both Mamba and transformer blocks to try and get the best of both worlds. It's clear this is just the beginning. Which, of course, leads us to the big, provocative question. Is this it? Is this the beginning of the end for the transformer's total dominance? Or, and this is what I think is really interesting, are we just at the beginning of a new hybrid future for AI? A future where we mix and match the raw power of attention with the sleek, incredible efficiency of Mamba. Honestly, we don't know yet. But one thing is for sure, the race to build the next generation of AI just got a whole lot more interesting.